Yeah, I can. I just, how do I exit full screen here?
Full screen. I am sharing the screen.
I know. I chose full screen, but atom is missing
Yeah,
essentially,
it's a
or I don't know, an
nitrogen
ion. I don't
vacancy.
know.
That's a typo. It's called the nitrogen vacancy center in diamond. Okay, so it's a kind. We take a ultra pure diamond, and what we do is we create a vacancy. This has been proposed for quantum sensor systems. So this is nitrogen vacancy. So it's a deterministic generation of nitrogen vacancy centers using chemical vapor deposition. Okay, so this has been recently done by research lab in Australia, and you must be aware of other techniques like the topological quantum computer, and NMR is the oldest one, nuclear magnetic resonance. So now I am trying to.
There. Sorry.
Yes, yes, Mario.
I I thought there was another one based on silicium.
Silicon-based quantum computing, right?
Yes.
Silicon-based quantum computing can be categorized as a quantum dot, I believe, or let me know if it is wrong. I think it is a quantum, silicon quantum computing.
It's an Australian
Yeah,
company,
it's
I
a
think.
quantum dot. Silicon is a quantum dot approach. Silicon quantum dot.
Okay.
That is the second.
Right. It's a company called Silicon Quantum Computing
Yeah,
from Australia.
that's right.
That is,
Called a CQD.
yeah, exactly.
Right. So that is becoming very popular. Even Intel and TU Delft, I think they are also trying on silicon-based quantum computing approach. Or Purdue University. I'm not sure if it is TU Delft or Purdue. So I'm trying to uh,
Okay.
summarize the quantum architecture after this. Basically, the quantum architecture, when you look at the bottommost layer, it is the physical layer where the manufacturing of the chips comes in, and then interfacing with the classical systems, sources of energy, and then building a instruction set. On the top of it, we'll have a quantum processor, and with consisting of an arithmetic logic unit, runtime, and a compiler. On the top of which we'll be running quantum software development kits. This is a reference architecture of the quantum computer. At the bottommost layer, we have the qubit storage and gate technology. How do we calibrate it? Then we build a multi-qubit on the top of single qubit systems. And then the wiring comes in, the interconnection between quantum gates. Then we build error correction and signal processing. On the top of it, we will build algorithms. This is a slightly old model. If you look at a more generic model, we can look at consisting of quantum applications at the top, and where we build logical qubits and logical gates. But the base layer is the physical layer, the hardware apparatus. The physical qubits, their calibrations and control operations, the input output, single qubit and multi qubit gates. Then the virtual layer, where we do the error cancellation, when we do the further precise measurements on the using the poly gates like X gate and the Z gates. Then we have then we virtualize the gates. We build virtual 1 qubit gates and the universal gate, C0 gate, and on the top of it we build the logical qubits. So we have physical qubits, virtual qubits, and logical qubits. So after the quantum error correction, we move to the logical qubits.
Gokul. What should I call you?
Yeah, Gokul.
Gokul or Alex? I don't know. Which one is your first name?
First name is Gokul. Alex is my surname.
Alex is your first name?
No, sorry, Alex is my surname.
Okay. Okay. So Gokul, can you go? I have a question.
Yes. Yes.
The previous 2 slides.
Pardon me? Do you want me to go to previous slide?
This one and the one before this.
Yeah.
Is both slides show the full stack, or is the next slide just part of this stack here?
These are 2 different visualization or different drawings. Basically,
Understand.
This is more generic. This slide is more generic, and this is more updated and more correct when you look at the practical scenario. So, for example, this is talking about the one thing very interesting is this is talking about the storage that we need to have a technology. This is talking about the real important criteria. So when you build a quantum computer, the qubit storage and the qubit gate modeling is very important, and it varies from one quantum computer to another. So this is very important point, but only from a hardware perspective. And interconnection is another thing. It's not very easy. Interconnection between quantum gates is very, very important. When you manufacture your qubit, when you calibrate your qubit, normally if you see, we use gold wires to make sure there is no interference, there is only limited noise. So these classical and quantum interconnection is mentioned here. These hardware related aspects are not detailed in this. This is more towards the modeling. This will help you to model the virtual layer, because the previous diagram doesn't talk about the virtual qubit construction. It just talks directly about error correction and the theory and the implementation of error correction in a generic. So this is generic when it comes to the top component, whereas this second diagram is more useful when you try to understand how to model the qubit. It's very important that you model the physical qubit into virtual, and then you on the top of the virtual qubits you implement the error correction, and on the top of it we build the logical quantum bits, and then on the top of it we build the applications.
Okay, understand. Thank you.
Sure. So this is a very simple summary of that diagram, right? We have quantum. At the end of the day, we are trying to build quantum registers comprising of quantum qubits interconnected in a channel. So this is very important, right? Because even if we are able to construct a large number of qubits, if we are not able to interconnect them properly, it will not be effective. That's why when you look at the interconnection topology in each of the architecture, for example, if you look at the IBM's 5-qubit architecture versus 15-qubit architecture, it varies significantly. And Probably I'll be able to show that in the next session. I will be taking you to the IBM's quantum machine.
Gokul.
Yes.
I have a question? I'm asking the question now. I don't know if it is a good moment to ask the question. You choose when you want to answer, okay?
Sure.
But my question is, you're talking about these connections. So I imagine I have a qubit which is in a certain state. And now I have a connection. I don't really understand that connection. So let's say, now I don't see your screen anymore.
Oh, are you not seeing it? I'm sharing it again.
I just see.
What is the method? I've just sent a link on what is the interconnection used in superconducting qubits. So it's part of the fabrication process. So this is essentially using some kind of amorphous dielectrics like with very less high resistance, so that diffusion happens. Essentially, this could be like it could realize a tunneling between. So we need to create a quantum mechanical relationship between these qubits. That is the reason it seems they are using dielectrics. But I have not gone in detail about these interconnections. I will also share more in the coming session. It's a very good question. I'll get more material on this. I've seen in some videos how they implement this interconnections. It's called QUIC, Quantum Interconnects.
You mean on YouTube or?
Yeah, from YouTube. YouTube, I've seen it because I don't have access to a practical computer here.
Okay. Quantum Interconnects.
It is called Quantum Interconnect, QUIC. I'll share more materials.
Right.
And probably one of the session we will detail it out.
Okay, sounds great.
QUIC. Yeah. Could you see that chat link I've shared in the chat?
Yeah, I received it. Thank you. Yeah.
Yeah. It's a very well designed. The first one is a detailed research paper. But this technology is only for superconducting qubits. It will differ when we do the ion trapped or the topological or the quantum dot based approach.
Right. Right. Okay.
So we'll continue into the presentation.
Oh yes, please. Thank you.
Sure. I'm sharing the screen again. Okay, so now we have seen the summary view of the quantum computer schematic. But how do we interface quantum computers with classical computers? For example, this year we have seen an experiment that Google has done in the Oak Ridge laboratory, right? Perhaps I could find an example of it online. The Google quantum experiment. This is on IBM Oak Ridge laboratory. So yeah, so basically this is called as the quantum supremacy experiment, famed quantum supremacy experiment after John Preskill, the famous computer scientist, quantum scientist, coined the term. Okay, so I think I'll also get some videos on YouTube. Yeah, so please let me show this video. Oh yeah, this was done. Hope you can see my screen.
Yes.
Yeah, this is on YouTube. This is the famous quantum supremacy experiment.
Quantum computers are excellent platforms for solving some of our physical science problems. This includes problems in chemistry, materials, and high energy physics. Quantum computing uses the physical properties of particles like molecules and individual atoms to process information. This gives access to new types of physics called quantum physics that enables us to accelerate the paths to solution. In order to test how well we're able to build quantum computers, we have to perform benchmarks that compare the performance of the quantum computer to conventional standards. As the world's fastest supercomputer, the Summit system provides an excellent standard by which to compare the quantum computer. The quantum supremacy benchmark compared how much time and energy it took to solve a problem on Summit compared to the same metrics on the quantum processor. And based on the fact that they both gave the same answer, we were able to then measure how long it took on the two systems. The Summit supercomputer system actually took longer to solve the same problem, but this was a quantum benchmark designed specifically to test that capability. Quantum supremacy is a milestone in the development of quantum computing, which indicates that quantum processors are able to equal or surpass conventional computing capabilities. At Oak Ridge, we see quantum computers as a type of accelerator that we can use for our future high-performance computing systems. Today's quantum processors haven't reached that point yet. We've only now been able to demonstrate that they're on par with our...
So this is a very interesting experiment. I will try to show another video on what happened
with our supercomputing systems.
This is a random sampling circuit. Random sampling circuit, quantum supremacy. Quantum. Yeah. This is something, it's very interesting. Google. Okay. Google has taken a session on this. Yeah, okay, random circuit sampling. Yeah, this is Scott Aronson. He's one of the most famous professors now. He actually wrote a very interesting article. There was a debate. Mario, you may be aware of this debate between IBM and Google on the claim of quantum supremacy. So when Google said...
Yeah, I heard of it, yes.
Yeah, when Google said they achieved quantum supremacy, then IBM questioned it. What Google said was they achieved something in 3 seconds or 300 seconds, which normally a supercomputer would take in 1,000 years. But then IBM who built that Oak Ridge supercomputer said, no, that's not correct. This could be done by the supercomputer in 2 days. So that was the debate, and Scott Aronson's blog on this, Scott Aronson's blog on this was really popular. Aronson on quantum supremacy. He has written an interesting blog post on this. Yeah, I think he has changed the... Okay. Yeah, so I'll come back to the presentation. So the point is we can do a lot of wonders using a quantum computer together with a classical supercomputer. For example, you can input a quantum circuit and you can do circuit partitioning in a classical supercomputer and then try to do a circuit simulation and combine the experiments. For example, quantum computer is able to do some task efficiently, like factoring a prime number or finding the polarization or the hybridization of a molecule or the any chemical behavior or any mathematical like graph isomorphism. We will use quantum computer only for specific measurement task. So that is written in the circuit, and then what we do is we partition that circuit. So for example, there is we construct a random graph using quantum computer. Right? We do a random walk. and then we can partition that graph, because for partitioning you don't need to use a quantum computer, right? You can do it through a classical computer, and then you can verify that process through. So the formal verification of that circuit partitioning can be done by supercomputer, and then you can combine the measurements. This is something I'm just thinking about a possibility, but there are separate videos on hybrid quantum classical computers which can give more details about it. I will try to take a separate session where we can discuss about this hybrid integration. So the next topic I am covering in the presentation is about basics of qubit, I think, which you are very familiar about, right? But I just wanted to mention it here. The different ways you can construct quantum bits. One way is using superconducting loops, the Google, IBM, uh, the Rigetti D-Wave approach. Honeywell and IonQ are working on trapped ion approach, where they're taking some specific ion, like calcium ions or calcium ion, and then passing it through an essentially passing through an electric field, and then controlling the electric field using a laser beam. The other approach is the silicon quantum dot approach by Intel and other startups. Topological qubit approach by Microsoft is the other approach in prominence now. So probably in from the next session onwards, I will definitely cover specific topics. We'll move away from generic topics to specific topics from next session. Hope we will slowly get more participation and attendance, and I will also become more regular. Today there was a hiccup in the time. I've shifted the time, and the meeting tool also I've changed. So hopefully we'll be able to